Title is recent advances.
Title is yeah.
Adventures in Young Algebraic
Something
Bethe
about Bethe
Ansatz.
Ansatz. Okay, so should I start? People are still staying. It seems it's switch on. Okay, so let me start my presentation. First of all, I would like to congratulate my friends and colleagues, Nikita, who is here, and Leonid, who is there, and also organizer of this nice meeting. So I'm going to talk today about Algebraic Bethe Ansatz, and I also would like to thank Nikita that he once introduced that time master student from High School of Economics, Andrei Lyashik, to Algebraic Bethe Ansatz. Is it true? Because they started coming here to discuss this subject, and Andrei now became a quite good specialist in this field. And my talk will be based on the recent works done with him. Several years ago, we with Nikita, Andrei, with Eric Ragusi from ANSI and Artur Gutsaluk produced some results in this field. I'm not going to talk about this result because Nikita is no these results, so I decided to talk about some of them. I will cite and show. But basically, I'm going to tell you about approach which we started to develop together with Sergei Khoroshkin, who is here more than 15 years ago, to Algebraic Bethe Ansatz. So my talk will contain basically two parts. This is outline, but these two parts, first part will be kind of introduction. So I will give you some ideas about this approach to Algebraic Bethe Ansatz, which use current algebras. And second part of my talk will be our recent result with Andrei, when we extended the beginning of this approach to other series, because it is well known that the Algebraic Bethe Ansatz was developed first for in the simplest case of rank 1 SL2 algebra, and most results were obtained there at the beginning. So I will start from general description. What is the general integrable system is? Usually, any quantum integrable system is described by monodromy matrix, which is n by n monodromy matrix. The matrix entries of this matrix are operators in physical in the Hilbert space of the model, and usually model to be solved by Algebraic Bethe Ansatz, the Hilbert space of the model should contain special reference vector, which is we call the vacuum vector, which is annihilated by lower part of monodromy matrix and eigenvalue of diagonal part, and so. So this is general formulations of general integrable models, but in order this system to be integrable, which means that it should contain enough number of commuting integral of motions, the monodromy matrix should have commutation relations, which is written here, which uses R-matrix. Some are R-matrix, and this R-matrix should, of course, satisfy Yang-Baxter equations. And Algebraic Bethe Ansatz means the construction of special vectors in Hilbert space of the model, which build from from upper monodromy entries acting on vacuum, and when this parameter t, which is called beta parameter, satisfies so-called beta equations, then such vector becomes the eigenvalue of transfer matrix. So solve eigenvalue problem in this integrable model. And the final goal usually final goal in integrable models is to calculate scalar product between beta vectors and dual beta vectors, and calculate form factors, because from this point, when you do this, then you can start really applications to some particular physical model. I'm not going to talk about some concrete particular models. I'm going to describe general the whole class of integrable quantum integrable models, which are related to some particular matrices associated with algebras of different series. As far as I know, this final goal of algebraic Bethe Ansatz was beautifully solved by Nikita in SL2 case in rank 1 algebra with this determinant formula for scalar beta vector scalar products, and this formulas has a lot of applications further, but it is again, it was only for rank 1 or SL2 case. Is I'm right? So please correct me if it's not. It was 79 paper, yes, or 89. Sorry, 89. Okay, still many years ago, and of course, there are development in the field related to other models, which is usually related to hierarchical Bethe Ansatz, but in this case, people usually get beta equations, but to describe beta vectors was quite difficult in this framework. So I would like to say that our approach really can solve the problem to build those beta vectors even before solution of beta equations. We call such beta vectors off-shell beta vectors. So just to describe this polynomial, and as I already told, I'm not going to talk about any particular integrable models. So I will talk about different integrable models classified by solutions of Yang-Baxter equations, and these solutions were described in trigonometric case by Mikio Jimbo many years ago, and he classified and present explicit form of R-matrix, the trigonometric R-matrix for all series of quantum affine algebras. Recently, there are many results on Yangians, on rational R-matrix, but I'm not going to show you these references. But if you are interested, you may see a recent paper by Alexander Molev and his team, who described the Yangians related to different series, and so for us, the main input are particular R-matrix, and we try to go as far as possible, just to use commutation relation between monodromy matrices, and to do this, to solve this problem, we use 3 facts. So I will just shortly count these 3 facts. First is that in the theory of quantum affine algebra and Yangian double, there is a description of these algebras which use so-called L operators, and commutation relation of this L operator are the same as in monodromy metric, in quantum integrable system, the same. So it means that in order, if we need to exploit only commutation relations for monodromy, we can use the commutation relation in these algebras because the algebra has many other properties which we can use to effectively use this commutation relation. Because even, okay, in SL2 case, this is easy, more or less easy to do. Nikita can explain. You may ask him, he will explain how to do in SL. In SLN case, it's already not so easy. And as a series, it almost becomes very complicated combinatorial problems. But the second fact is that all these algebras, quantum affine algebras or Yangian doubles, has another realization in terms of Cartan-Weyl generators, which is called Drinfeld or current new realization of these algebras, and relation between them, between R-matrix approach and or L operator approach and current approach is very simple. Relation goes through Gauss decomposition. So you decompose monodromy matrix or L operator of the corresponding algebra, and then linear combination of this Gauss coordinate are so-called currents, and commutation relations for these currents are much simpler than original commutation relation of L operators and can be used. And for, the third part actually was the cornerstone of the approach developed together with Sergei Haroshkin, is that there is a special, okay, so this algebras has two descriptions. I will explain later what kind of descriptions I mean. This algebras has different type of Borel subalgebras. Again, I will explain later what does it mean. And this different type Borel subalgebras has intersection, non-trivial intersection, and there is projection on these intersections such that one can relate Cartan-Weyl generators or currents and Gauss coordinate through these projections. And beta vectors, off-shell beta vectors itself is projections of the product of the currents depending on beta parameters, and you have to use only simple root currents which appear naturally in this Drinfeld new realizations. So this is main ideas for that, and actually maybe Sergei can answer. So this idea about the fact that beta vectors is projections of a product of currents, I learned from you. Is it your idea? Is it true? Okay, so this is Sergei Haroshkin idea that you can use Cartan-Weyl basis to describe off-shell beta vectors. So I will give short sketch of what we can do in A series for GLN case algebras, and then at the end of my talk I will show you what can be done in other series. So R matrix for in GLN case, everybody knew this expression, can be written in such nice form with rational functions depending on the spectral parameters, and we call this algebra loop algebra because we do not need a central element of quantum affine algebra, because in quantum integrable models you of spin chain like you never use this central element of a quantum affine algebra. So the algebra itself generated by modes by these elements L, I, J, plus minus n. N is non-negative, and with some restrictions. And you gather this generator into series. You compose the series into matrix, and then this matrix satisfy RL relations, and plus minus the superscript corresponds to Borel subalgebras of the algebra. So then the first paper on this field about isomorphism between R-matrix realization of quantum affine algebra of this type and Drinfeld realizations appear 93 last century by Ding, Gentai Ding, Igor Frenkel, and they exactly proved that the Drinfeld realization is equivalent to RL realization for Euclidean algebra if you introduce currents as linear combination of Gauss coordinates, and then commutation relations in currents will look very simple, like vertex type algebra, of course, plus SER relations, which are important, also important, but I'm not going to these details now. So, so idea is to, if you want to calculate something between beta vectors, I mean, when you calculate beta vectors, for example, eigenvalue problem, you need to commute elements of monodromy matrix. So it's very complicated combinatorial problem in general situation. So idea is to replace this generator by the current generators, and since the commutation relations looks quite simpler, then there is a hope that you can do these calculations quite easily. So, and behind this approach, there is a deep mathematical background, which was described by many people, but I knew this from Sergei Kharoshkin and Valery Tolstoy, who described the relation between Drinfeld realization and for quantum affine algebras, and they described so-called natural ordering in Cartan-Weyl basis in this algebra, and it says that if your generator E gamma correspond to the root gamma, which is sum of two roots alpha plus beta, then you have two natural orders, or this or this, and it means that you have natural and the commutation relation in general for arbitrarily composed roots looks like this, which means that you have subalgebra, all the subalgebras in this Cartan-Weyl basis, and this is my famous animations which show how the Cartan-Weyl generators, which we built from the Chevalier basis, turns to be current generators of the algebras. I give this example for SL2 because it is two-dimensional place, because otherwise it's very difficult to draw. So in SL2 case, you have two Chevalier generator, E alpha 0, E alpha naught, and I put this these roots as these vectors. And after first commutations, you have several relations between them. After first commutations, you have so-called generator corresponding to imaginary root. Then you permit to do next commutator to get this generator, but third generator is forbidden by SER relations. But then you can proceed further and get infinity number of generators in that directions. You can do the same with negative simple roots and produce negative composed roots. Then the standard decomposition to standard Borel subalgebras is shown by this line, and there is a theory that actually it is not unique choose of Borel subalgebras. You can somehow rotate this this line, which corresponds to so-called twisting of the algebra. I'm not going to these details, but there is extreme case when all non-imaginary real roots looking down are below this red line. The pointer is very slow, and other roots are above. And this decomposition of the whole algebra into two Borel subalgebras is called current decomposition, and corresponds to, so these generators are current generators can be gathered in the currents, and this is the meaning of the results obtained by Sergei Kharoshkin and Valery Tolstoy. In Yangian case situation a little bit more complicated because there is no this decomposition is to positive and negative Borel-Sabalja is more complicated, but it's just to mention, and all this leads to extension of the ordering in the positive and negative Borel-Sabalja, standard Borel-Sabalja, to the cycle ordering of all roots of all generators corresponding to all composed roots in this algebra. So roughly speaking, you have generators corresponding to current EI. I count the simple roots of the underlying simple algebra. These are Cartan, and these are corresponding to negative roots. And there is a cycle ordering. It seems that there is a paper by Beck, probably Sergei will correct me, who described this cycle ordering. And this ordering actually gives you a quite powerful tool how to calculate projection, which I mentioned above. And this is again just the same picture, which shows how interrelate these different Borel subalgebras, and that they have non-trivial intersections. And we should remember also that these algebras are Hopf algebras, and when you twist algebra, your Hopf co-product structure is changing. And for the Drinfeld realization, you have such co-product, and in R-matrix approach, the co-product is like this. And as I told, you can consider the intersection between current or Drinfeld Borel subalgebra and standard Borel subalgebra, and define the projection quite in universal way through co-unit map in the Hopf algebra, and finally prove the properties of these projections, which were proved by our joint paper with Sergei Kharoshkin and Benjamin Enriquez 15 years ago. The first is that you can always, using this projection, you can, if you have the element from the Borel subalgebra, actually from some completion of this Borel subalgebra, but it is just details, you can always normal order according to cycle ordering the product or any element from this current Borel subalgebra. And beside this, this projection describe the relation between standard and Drinfeld coproduct. This is just consequence of this twisting procedure. And all this actually give you already all necessary tools to calculate beta vectors in terms of Cartan-Weyl basis. This is just notations. In next formulas, they will be ugly, so I should warn you. But don't pay attention, because I just want to give you some impression how it works. The scalar function, which depends on the set of variables, means the product. So these notations was invented by Nikita. And very, very helpful to do calculations. Otherwise, to write all these indices, and it is completely mess. Okay, so as I told, by Sergei Kharoshkin idea, the beta vectors, off-shell beta vectors, is the product of the currents, specially ordered with some precise coefficient to which take care about poles and zeros, etc. And when we start to work with Sergei, we published the paper in this paper where we found a way how to calculate this collection, how to calculate this projection, and how to re-express the result of these calculations in terms of monodromy in terms of entries of L operator or monodromy matrix element. So it was quite good results. I did not write the answer. It could be written, but I did not do this by purpose because it's very difficult to use this result because you have expression, a huge sum of over permutations of all indices, and what to do with this. But nevertheless, using these descriptions, you can easily describe, for example, hierarchical relations between beta vectors. For example, like this. So this is hierarchical relation between beta vectors for GLN with beta vectors for Bn-1 algebra. And the idea is very simple. Since we know that beta vectors is projection of the currents, we select this product of GLN-1 currents, apply this normal ordering procedure with using projection, and then you just need to commute the total currents with these negative projections and get this result. So this is how hierarchical relation in this approach looks like, and this is example how, for example, for GL3 beta vectors looks like. So it is given by the product of these entries of L operator, and sum is given by the partition of the set of beta parameters with the only restriction that cardinality of this subset should be equal to cardinality of this subset. But again, using these formulas, we got several nice results together with Nikita and our colleagues. Even in some cases, we even got some determinant formulas. I'm right, yes? Some particular models, but in general situation, this formula just useless. But instead of that, we start to think how to address the problem on scalar product, for example, in general situation. And we found that to do this, we don't need actually the formulas for the beta vectors, but what we need the formula for the action of monodromy matrix element onto beta vectors. And we found this for GLN case explicitly, how monodromy entries act on beta vectors and produce linear combination of these beta vectors with some explicitly prescribed coefficients, and the result is sum of a partition of the set of beta parameters. So using this action, you can easily verify that that monodromy that such beta vectors becomes eigenvector if beta equations are satisfied, and to prove this action formulas, we developed so-called zero modes method, which is based on this RLL commutation relations between zero modes and L operator, which allows, so this commutation relation allows you to get this action formula from two facts, from the action of zero modes to beta vectors and action of extreme entries of monodromy matrix to the beta vectors, which is very simple. Again, the fact that it is simple, very easy to prove in this approach through Cartan-Weyl generators. I skip the details. So finally, we found using the action formulas, they can be reinterpreted as a recurrence relations, which relate beta vectors with bigger number of beta parameters and with smaller number of beta parameters. And using the zero modes method, Nikita, we were succeed to add additional beta parameter inside of the sets. You remember, you prove this result for the first and the last sets of beta parameters, and your proof was based on Hierarchical Bethe Ansatz and contained several pages and was very, very heavy. In this approach, calculations are much simpler, but and we can these results. And now we can use these results to address the problem for scalar program. We define dual beta vectors. We define the scalar product in terms of so-called highest coefficients. Again, details can be found in our joint papers. And then the idea to calculate the scalar product, idea is to calculate this highest coefficient functions, finding for them recurrent relations. And this sometimes this could be done. The idea is very simple. So you consider a scalar product C and B. So you select one beta parameter. Then you use recurrence relations for dual vector C. Select this monodromy element, and then act by this monodromy element to the vector B. And finally you may get the recurrence relations for this highest coefficient. Again, to solve this recurrence relation, it's another problem. It's rather difficult, and I mean, in some particular cases, maybe it can be solved and get some determinant forms. This we yet, and I hope in the future, maybe if we will come back to our collaboration, maybe we will address this problem for other series as well. Okay, so I now start. So I have still some minutes, yes. I will start the second part of my talk about the other series. So if you look carefully to Jimba's R matrices, then you will see that they can be written in the same form for all these algebras, B, C, D, A, and the twisted A. The difference will be in size of the fundamental representations, parameter xi, map I, and some sign function epsilon. So they are written in this slide. And for all these algebras, R matrix will look the same. It will be just the sum of three terms, one as usual, P as A series, and Q. And so if you compare these formulas with Jimbo original formulas, you will be really, it was Andrei Lyashik who noticed this. Simplicity, actually, not him, I'm wrong. So actually this form was written in Alexander Molev papers. Yeah, Alexander Molev paper. And okay, so in the scaling limit, if you want to go from trigonometric matrix to the Yangian to the rational case, you easily reconstruct from this trigonometric R matrix rational R matrix, which can be used for the rational integrable models. But then using the properties of R matrix, you may, and using the commutation, so commutation relation now looks like this. So you complete mess. If you try to apply this, it's very complicated. And because of this presence of this pole in R matrix, you can easily prove that there is a central element Z in this algebra, which is product of transpose, L operator, twisted, and original L operator. So if we introduce this L hat and set the central element to 1, then we will have relation between L hat and L. And we can check that L hat also satisfy Young-Baxter equations with the same R matrix. And actually, it means that we describe the automorphism of the algebra to itself, the mapping from L to L hat. But this equality allows you to reduce the algebraic dependent generators in the algebra. So because in this BCD algebra, you have L operator, roughly speaking, 2n for rank n algebra, you have matrix of the size 2n times 2n. So you have twice more generators in this algebra, and these relations allows you to effectively reduce the generators. And okay, this is just Gauss decompositions, how they looks like for if we use the same. And actually, this was I never when we did the job with Sergey, everything perfect worked for SLN for A series, and I cannot imagine that this Gauss decomposition perfectly works in BCD series, and it was Alexander Molev and his team who did the job. And they said use the same Gauss decomposition and everything will work. So actually, what we did in this part, we just carefully read this paper by Alexander Molev team and found that that we can use this Gauss decomposition. And since L and L hat are related by transposition and inverting, which it means that you can easily relate relation between Gauss coordinates. So you just have to invert triangular matrices, which is very easy. But the problem is that if you want to equate L and L hat, the ordering of operators are opposite in these two expressions, FKA and here EKF. So you need to reorder in one of directions if you wish to solve this equality. And we can do this. And finally, we have so-called embedding theorem, which says that if we defined reduced monodromy matrix M ij for ij between 2 and n minus 1, then because of this Gauss decomposition, for this reduced monodromy matrix, we have expression which looks like quantum, almost looks like quantum minors, and we can prove the theorem that the commutation relations for M follows from the commutation relations for L, with R matrix corresponding to the smaller algebra. And this was done. This proof of this theorem was done in our recent paper for all ABCD algebras simultaneously. And this is very nice because the R matrix looks similarly. And this theorem, meaning of this theorem is that in order to apply all this construction in BCD integrable models, you need to have exact isomorphism, Frenkel-Ding isomorphism between L operator description and current descriptions. I'm finishing. Okay. Of course, it is written somewhere in the papers, but we need this to repeat these results to write this explicitly. And how to prove that this is isomorphism? It's very difficult because the commutation relations for big rank algebra is very complicated. But if you have this theorem, then you need to check only smallest commutation relation in smaller rank algebras in each of these series, BCD. And then if you do this, then by this theorem, these commutations will be reproduced in higher rank. So this is a sketch of the proof, which I skip. And so finally, each algebra in the current realizations is described by n-1 pairs of EQ-JLN currents plus dependent current because of this relation L hat L, and some additional current Fn En, which correspond to special root in Dynkin diagram on each of this algebra. And there is a difference for different BCDA2 algebras. It is details, but finally we can prove the relation between currents, these currents introduced in the previous slides, and Gauss coordinates of the corresponding monodromy matrices. So now we have everything to start applying this technique for BCD integrable models, and this is my conclusion and further plans. First of all, we have to, there is one more algebra in Jimba list, which is called D to N, and R matrix in notation of my talk looks even more complicated. And now we are working with Andrei on this algebra and hope to get the same results. The embedding, there will be much more interesting how the smaller algebra dn-1 is embedded in dn, but this is for the future conferences maybe. And so after that we can repeat all this zero mode method, etc., and hopefully to apply this result for calculation scalar product form factors, and maybe even use Nikita Solonov's expertise to work in BCD series. So that's all. Thank you.
Thank you, speaker. Any question or comments?
As far as I understand, the scalar problem is still for future.
Yeah. This is for future.
You did not study.
Yeah. We have a lot of.
You need some assistance.
Yeah.
Probably.
Yeah.
Okay.
Yeah. So we just produce some preliminary results which help us to
start to work.
Yes.
Okay. Thank you.
Another questions or comments? If not, then thanks, speaker, again. Now our next speaker, Sergey Haroshkin.